This video provides an introduction to sample size calculations. We perform sample size calculations to avoid sampling too many respondents and with that wasting valuable resources. But on the other hand, we also do not want to end up with too small of a sample as it may diminish the utility of the results. One type of sample size calculation is called a precision analysis. We perform a precision analysis to calculate the minimum required sample size to estimate a certain population parameter and to limit the risk of error in our estimate. This is what the formula for a precision analysis looks like. The n is the required sample size. The p is the expected proportion of the event of interest, and d is the margin of error. In this example, we want to know what the current contraceptive prevalence rate is among Dutch women aged 15 to 49 years of age. We start with determining the expected proportion P, which means that we need to define what we expect the contraceptive prevalence rate to be. We can determine this based on the literature, based on expert opinions, or based on a pilot study. If we really have no idea and we want to be on the safe side, then we assume to find a proportion of 50% or 0.5, as this will yield the most conservative sample. Step 2 is to determine our margin of error. This depends on the width of the confidence interval around the estimate, which is commonly 95%. A 95% confidence interval corresponds to a 5% margin of error. If we fill in all this information in the formula, so a p of 0.5 and a margin of error of 5%, our required sample size will be 384. We need to randomly sample 384 Dutch women to accurately estimate the contraceptive prevalence rate in this population. We also have a power analysis. A power analysis is performed if we want to determine the minimum required sample size to estimate a certain difference between groups. Let's say that we want to know the prevalence of anemia among women is different for women living in high altitude areas as compared to women living in low altitude areas. When answering the research question, there are two errors that we can make. We can make a type 1 error if we find a difference in the prevalence of anemia between women living in high and low altitudes when in fact there is no difference. In this case, we find a statistical association when it does not exist. In essence, it's a false positive test result. We also run the risk of a type 2 error. A type 2 error occurs when we fail to find an association between the prevalence of anemia and altitude, when in reality an association exists. In this error, we fail to detect a statistically significant association. We call this a false negative. A power analysis consists of the following ingredients: the margin of error, the power of the study, the standard deviation of the parameters, and the expected difference between the groups you are comparing. The margin of error, also referred to as the alpha or the level of significance, it is actually the chance to obtain a type 1 error, the chance that we find an association if one does not exist. We usually set this at 5%. In this example, it would mean that if we find an association between anemia and altitude, there is a 5% chance that this association is incorrect and due to chance. The power is the chance of finding an association if one exists. This is usually 80%. In this example, it means that if there is indeed an association between anemia and altitude, there is an 80% chance that this study will find it. We also try to estimate the variance in hemoglobin or altitude. And finally, we need to define the expected difference in the prevalence of anemia between women living in higher and lower altitude. This is how each ingredient influences the sample size. If we want a lower margin of error, and as such more confidence in our finding, we need to increase our sample size. If we want a higher power, we also need to increase our sample size. If the variance in the parameters is higher, we have to increase our sample size to be able to detect an association. And finally, the larger the difference between the comparison group, the smaller the sample size, as it is easier to estimate a very large difference than it is to estimate a very small difference. And finally, you may want to increase your sample size based on the design effect. If we use a different sampling strategy other than simple random sampling, we have to account for that in our sample size. We may also want to account for non-response. We usually assume a 10% non-response. We do this to ensure that we not use valuable power due to non-response.